Somewhere aboard a ship that has not been built yet, a child will take their first breath, having never felt real wind, never watched a true sunset, never once stood on ground that wasn't curved metal spinning to fake the pull of a world. That child will call the ship home, because for that child, it will be the only planet that has ever existed. This is why crossing the gap between stars turns out to have very little to do with engines, and almost everything to do with squeezing every function of an entire living world into a sealed hull that has to keep working long after everyone who built it is gone. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. A rocket can carry a handful of people to another world inside our own solar system in a matter of months. Push far enough, toward Mars or one of the icy moons further out, and the trip might stretch to a couple of years. That is difficult, but it is a problem with an ending. Supplies are counted, a return window is chosen, and everyone aboard can picture the day they step outside again. An interstellar ship cannot picture that day, because nobody currently alive on it will ever see it. The nearest star beyond our own, Proxima Centauri, sits about 4.24 light-years away. Light itself takes that long to cross the gap. Any physical ship, built from real metal and carrying real people, will take enormously longer. Even a vessel that somehow reached 1/10 of the speed of light, a pace far beyond anything currently flying, would still spend more than 40 years crossing that distance alone. Slower, more realistic propulsion stretches the journey into centuries. A civilization that wants to reach another star this way is not really building a spacecraft. It is building a nation that has agreed to be born, raised, grow old, and eventually pass on entirely inside a metal shell, without ever setting foot on the destination its ancestors chose for it. Every person who boards at departure will end their life somewhere along the route. Every person who eventually looks down on the new world will have been born after the ship left, will have never known Earth firsthand, and will have inherited a mission rather than chosen one. That is the detail that quietly changes the entire engineering problem. A crew capsule only has to keep people alive. A generation ship has to keep a society alive, across timescales, usually reserved for entire civilizations, back on solid ground. It has to replace weather, replace soil, replace the ocean, replace the atmosphere, replace the slow correcting machinery that an actual planet performs automatically and invisibly, second by second, for free. Earth recycles its own air, using oceans, forests, and a thin blue shell of atmosphere so vast that a single human breath barely registers against it. A ship has none of that scale to hide behind. Every gas exchanged by every lung, every plant, and every machine inside the hull has to be tracked, filtered, and returned, because there is no larger world nearby willing to absorb the mistake. This is the strange inversion at the center of interstellar travel. The distance between stars is often described as the hardest obstacle, and in terms of raw physics, it certainly is. But the harder practical obstacle may be much smaller in scale and far more mundane. It is keeping a sealed box of people breathing comfortably for 200 years without a single unrecoverable failure. It helps to understand why the trip takes so long in the first place, because the answer is not a lack of ambition, it is the plain arithmetic of energy. Accelerating even a modest ship, holding a few thousand people and everything they need to survive, up to a meaningful fraction of the speed of light, requires an amount of energy that dwarfs anything humanity currently produces in a year, let alone in the brief burn of a single launch. Chemical rockets, the kind that carried the first astronauts off the ground, are hopelessly inadequate for this task, since the energy stored in their fuel is tiny compared to what interstellar travel demands. Serious proposals instead look toward nuclear fusion, where the same reaction that powers every star in the sky is coaxed into a controlled burn aboard the ship itself, releasing enormous energy from a comparatively small amount of fuel. Other proposals go further still, suggesting that matter and antimatter might one day be combined in carefully controlled amounts, since that reaction converts fuel into energy more completely than almost anything else physics allows. A very different family of designs abandons onboard fuel almost entirely, instead unfurling an enormous sail and pushing the ship forward using a colossal laser array left behind near the home star, essentially throwing light at the ship instead of carrying propellant with it. Each of these approaches solves the raw energy problem in a different way, and each comes with its own trade-offs in mass, complexity, and risk. But even the most optimistic version of any of these technologies still points toward the same uncomfortable conclusion. Reaching another star system will likely take decades at the absolute best, and far more plausibly, centuries. Once you include the years spent accelerating at the start of the journey and the years spent slowing down again near the end, there is no shortcut waiting just beyond our current engineering. The distances involved are so large that even doubling or tripling our fastest achievable speeds only trims the trip from many centuries to merely several, rather than shrinking it down to something a single human lifetime could comfortably span. Once that reality is accepted, the entire shape of the mission changes. You stop designing a fast trip and start designing a slow, permanent one, and permanence is what forces every other system aboard, air, water, food, and everything else, to behave less like supplies and more like an entire living world in miniature. It is worth pausing on why anyone would choose this particular approach at all, rather than one of the alternatives that get discussed alongside it. One option sometimes proposed is sending people in a deep, suspended sleep, slowing their bodies down for the length of the crossing, so that only a few years of biological time pass for the crew, while centuries pass outside. The idea is appealing, largely because it avoids the entire problem of multiple generations living and passing on aboard the ship. The trouble is that nothing resembling reliable, long-duration suspended sleep for human beings currently exists, and even optimistic research into the idea suggests it may only ever extend safely to a period of months or a small number of years, nowhere close to the centuries such a voyage would demand. A second option removes people from the equation almost entirely, sending only robotic probes to explore and report back, without any crew at all. This makes enormous sense for scientific exploration, and it is almost certainly how humanity will first learn anything real about other star systems. But it does not answer the deeper question a generation ship is actually trying to answer, which is not how do we learn about another star, but how does a living, breathing, human community eventually come to exist around one? A generation ship remains, for now, the only approach built entirely from technology and biology we already understand, at least in principle, however difficult it remains to actually build. It does not require inventing new physics, only scaling up systems already partially proven, life support, closed agriculture, nuclear power, and rotating structures, into something durable enough to run without failure for far longer than any of them have ever been tested. That practicality comes with a heavy ethical question attached to it, one that every serious proposal eventually has to confront directly. The people who volunteered aboard such a ship are making a choice for themselves. Their descendants, born decades or centuries later inside the hull, are not making any choice at all. They inherit the voyage the way a person inherits a family or a home country. without ever having been asked whether they wanted it. Some thinkers who have studied this question closely argue that this makes the entire project ethically troubling from the very start, since it commits potentially dozens of future generations to a life they never agreed to live, confined inside a structure they can never leave. Others argue that every child born anywhere is, in exactly this sense, born into circumstances they never chose. A family, a country, a set of historical conditions entirely outside their control, and that a generation ship is simply an unusually visible and unusually deliberate version of something already true of every human birth in history. There is no settled answer to this question, and it likely deserves far more attention than it usually receives in discussions that focus mainly on engines and life support. Whatever conclusion a future civilization eventually reaches, it seems certain that any serious attempt to build such a ship would need to think as carefully about the ethics of the generations born aboard it, as it thinks about the chemistry keeping their air breathable. Choosing where to point the ship in the first place turns out to be its own difficult problem, long before anyone starts worrying about air or water at all. A destination star needs to sit close enough that even a multi-century voyage remains within reach, which immediately rules out the overwhelming majority of stars in our galaxy, leaving only a relatively small number of nearby candidates within a few dozen light-years. Among those nearby candidates, the star itself has to behave well over long timescales, avoiding the kind of violent flares that some smaller, cooler stars are prone to producing, since a planet constantly bathed in dangerous radiation from its own star offers little advantage over simply staying aboard the ship. Then comes the harder question of what actually orbits that star. Even with our best current telescopes, confirming that a distant world has a breathable atmosphere, a stable climate, and conditions gentle enough for unprotected human life remains extraordinarily difficult from this far away. A mission planned to last centuries cannot simply aim for the nearest plausible-looking dot and hope for the best, since discovering upon arrival that the target world is unsuitable would leave a population with nowhere else realistic to go. Distance itself has to be weighed against suitability in a way that rarely produces a single, obvious answer. The very nearest star systems might turn out to hold nothing resembling a suitable world at all, while a slightly more distant system might hold something genuinely promising, forcing planners to decide whether a marginally longer journey is worth the improved odds of actually finding somewhere survivable when the ship finally arrives. That trade-off, distance against likelihood of success, sits at the very foundation of the entire mission, decided long before the first support beam of the hull is ever assembled. Even the definition of a suitable star itself would need careful thought, since not every star that looks stable over the short timescales we have been able to observe from Earth is guaranteed to remain stable across the many additional centuries a ship would need to spend traveling toward it and settling in around it afterward, which means planners would need to lean heavily on stars already known through long observation to behave consistently over timescales far longer than a single human lifetime. This is part of why many serious proposals imagine sending fast, lightweight probes ahead of any crewed ship by decades or more, using them to scout candidate systems in detail long before committing an entire population to the multi-century journey required to reach one. Some designs go further, suggesting the ship itself should remain flexible about its exact destination for as long as possible, capable of adjusting course somewhat during the early years of the voyage if new information arrives from probes or updated observations back home, rather than locking in a single unchangeable target the moment it leaves. Even the criteria for a good destination shift once you consider that the ship's population may not be trying to recreate Earth exactly, but simply trying to find somewhere survivable enough to finally step outside of a metal hull. A world slightly colder, slightly thinner in its atmosphere, or slightly different in its gravity than Earth, might still represent an enormous improvement over centuries spent inside a sealed structure. Provided the population arrives prepared to adapt rather than expecting to find a perfect twin of the planet their ancestors left behind. Choosing exactly who boards at departure turns out to matter just as much as any question of ethics, since the founding population effectively sets the ceiling on what the ship's society can become for centuries afterward. Physical health and genetic diversity matter, but so do skills, and not simply skills in the narrow sense of a single trade practiced well. A founding population would need farmers, doctors, engineers, and machinists in genuine depth, but it would also need teachers capable of passing every one of those skills faithfully on to children who may never meet anyone from Earth to correct a misunderstanding years later. Psychological resilience matters as much as any technical qualification, since the founding generation is being asked not simply to endure a difficult journey themselves, but to model, for every generation that follows, what a stable, functioning life inside a sealed hull actually looks like. Some proposals suggest the selection process would need to favor cooperative, even tempered personalities over purely individual achievement, since a population of brilliant but difficult people, spread across a small, closed community with nowhere to escape to, could prove far more dangerous over centuries than a slightly less spectacular population capable of getting along. Age matters as well, in ways that might seem counterintuitive. A population made up only of young, healthy adults at launch would eventually age together, all reaching old age around the same decades, straining medical and caregiving capacity all at once, rather than spreading that burden evenly across time. Many designs, therefore, favor a founding population deliberately spread across a range of ages, along with careful early planning for when children are born, specifically to avoid the entire ship lurching later into a single, overwhelming wave of elderly care, followed by a generation gap with too few young workers to support them. Balancing ages at departure also helps smooth out the transfer of accumulated experience, since a population made entirely of newcomers to every task would lose valuable practical knowledge far more slowly if seasoned. Experienced individuals remain available to mentor and correct the younger workers, taking over critical roles for the very first time. None of this can be planned perfectly in advance. Beyond individual selection, the overall balance of skills across the founding population matters just as much as the qualities of any single person chosen. Since a group heavily weighted toward one profession, while lacking depth in another, could leave the ship dangerously exposed the moment that missing expertise turns out to be urgently needed, perhaps decades after departure, when no adjustment to the original selection is possible anymore. Planners would likely need to model not just what skills the ship requires at launch, but what skills its society will need to keep producing internally for centuries afterward. Teachers of teachers of teachers. Each generation responsible for successfully passing every essential capability forward to the next, without any margin for a skill, quietly slipping away simply because nobody thought to keep training people in it. But it illustrates, one more time, the same underlying truth running through every part of this project, that the ship is never really just a machine being engineered. It is a small civilization being deliberately founded, with every choice about who joins it shaping what kind of civilization it eventually becomes. Consider what that means for something as basic as air. On Earth, you inhale oxygen and exhale carbon dioxide without a second thought, because forests, algae, and oceans are quietly converting that carbon dioxide back into oxygen somewhere over the horizon. You never see the machinery. You never think about the fact that a rainforest on the other side of the planet is part of the reason your lungs work tonight. Aboard a generation ship, that invisible partnership has to be rebuilt from scratch, inside a hull that might only be a few hundred meters across. There is no ocean to buffer a mistake. There is no forest downwind to quietly fix an imbalance. Whatever air exists at departure is, in a very real sense, the only air that will ever exist for that ship, cycled and recycled for as long as the journey lasts. Engineers describe this as a closed-loop life support system, which sounds tidy on a diagram, 3 boxes and some arrows. In practice, it means banks of algae, tanks, chemical scrubbers, and mechanical separators working around the clock to strip carbon dioxide from the air and split water into breathable oxygen. It means humidity has to be pulled from the air constantly, because thousands of people breathing, cooking, and washing inside a sealed volume will fill that volume with moisture far faster than it can be tolerated. It means trace gases nobody thinks about, the faint chemical residue from plastics, cleaning products, paint, and machinery, have to be filtered out before they slowly accumulate into something toxic. None of this is exotic technology. Versions of it already exist aboard orbiting space stations today. The difference is duration. A station's life support system has to run reliably for months at a time, with resupply missions and fresh equipment arriving regularly from the ground. A generation ship's system has to run for centuries without a single resupply flight because there is no ground to send one. Every filter, every pump, every seal has to either last for the entire voyage or be repairable using only what the ship carries with it. That single requirement rewrites the entire design. You cannot simply install the best life support hardware available and call the air problem solved. You have to install redundant systems, and redundant systems for those redundant systems, along with the raw materials and trained hands needed to manufacture spare parts that were never anticipated at launch. A blocked filter on Earth is an inconvenience. A blocked filter multiplied across an entire population, with no replacement available and decades left to travel, becomes the difference between a functioning society and a slow disaster. This is why the air inside such a ship would likely be the single most heavily monitored substance aboard, checked constantly for oxygen levels, carbon dioxide buildup, humidity, and dozens of trace contaminants that would mean nothing to a person on Earth, but everything to a population that cannot simply step outside for a breath of something fresh. There would be no outside. Some proposals lean heavily on biological help for this task, growing dense tanks of algae or other fast-growing organisms, specifically because they convert carbon dioxide back into oxygen efficiently, essentially recreating in miniature the exact service forests and oceans provide for free on Earth. Other designs favor purely mechanical and chemical scrubbing, using equipment that strips carbon dioxide from circulating air through chemical reactions, with no living organism involved at all, valued mainly because mechanical systems can sometimes be made more predictable and easier to repair than a living culture of algae that might itself fall ill, starve, or behave unexpectedly if its own conditions drift even slightly out of balance. Most serious designs end up favoring some combination of both, precisely because relying entirely on one method means a single point of failure could threaten the entire population's air supply at once. If the algae tanks were the only method of producing oxygen and something went wrong with them, whether disease, contamination, or simple neglect during a difficult period, the entire ship would have no backup while a new culture was cultivated back to health. If purely mechanical scrubbers were the only method, a critical parts shortage or an unexpected chemical failure could leave the population with no biological buffer to fall back on while repairs were made. Layering both approaches together means a failure in one system buys time rather than triggering an immediate crisis, giving engineers room to repair the failing component before the backup system's own limits are reached. The hull would be the entire sky, and everyone living beneath it would depend on that recycling loop holding steady, breath after breath, for longer than most nations on Earth have existed. Water raises the same problem in a different shape. Earth holds an ocean of it, endlessly evaporating, falling as rain, running through rivers, and returning to the sea in a cycle so large that a single drop can spend thousands of years moving through it. A ship carries no ocean. Whatever water is loaded before departure has to serve every shower, every meal, every crop, and every person for the entire crossing, which means almost none of it can ever truly be lost. Sweat evaporates into the air and has to be pulled back out through humidity control. Wastewater has to be filtered, treated, and returned to drinking quality again and again, indefinitely. The same water that once passed through someone's kitchen sink might, decades later, pass through their grandchild's shower, having been cleaned so many times that its history has become unknowable. That sounds unpleasant, only because we are used to a planet generous enough to hide the process. Rain already fell through the atmosphere, soaked through soil, and passed through countless plants and animals before it reached the tap in your kitchen. The ship simply removes the scenery and leaves the plumbing exposed. Waste follows the same unforgiving logic. On Earth, waste can be buried, burned, or handed over to bacteria and time, all working somewhere far from where you live. Aboard a sealed ship, waste is not something to get rid of because there is nowhere to send it. It has to become an input again, broken down and returned as fertilizer for crops, as material for manufacturing, or as feedstock for the microbial systems keeping the water and air loops balanced. Nothing can be treated as garbage in the way we casually use that word on Earth, because garbage assumes somewhere else exists to receive it. For a generation ship, there is no somewhere else. There is only forward. Turning wastewater back into drinking water usually happens across several distinct stages rather than in one simple step, since no single process can reliably remove every kind of contaminant on its own. Solid material is separated out first. Then the remaining liquid passes through filters fine enough to catch bacteria and other microorganisms. Then, through additional chemical or biological treatment designed to break down anything organic that slipped through the earlier stages. And finally, through a distillation or similarly thorough purification step meant to catch whatever the earlier stages missed. Every one of those stages needs its own monitoring, its own spare parts, and its own trained operators, since a failure anywhere along that chain could mean water reaching people's homes before it has been fully cleaned. Redundancy shows up here just as it does everywhere else aboard the ship, with backup treatment lines ready to take over if a primary line needs repair, and with stored emergency reserves of clean water held aside specifically to cover the gap while any serious problem in the treatment chain gets fixed. Continuous sensor monitoring would need to track water quality at multiple points throughout this entire chain, checking for chemical contamination, unwanted microbial growth, and subtle shifts in mineral content that might otherwise go unnoticed until they had already affected the health of everyone drinking from that supply. Unlike a city on Earth, where a contamination event can be addressed by temporarily importing bottled water from elsewhere while the problem is fixed, a ship facing a serious water quality issue would have nowhere else to turn, which is precisely why these monitoring systems would need to catch problems early, quietly, and reliably, long before they ever became severe enough for residents to notice anything wrong simply by turning on a tap. This turns the entire vessel into something closer to a single, continuous organism than a machine. Every system depends on every other system, and pulling on one thread changes the tension in all the others. Add more people, and the water loop and air loop both feel it immediately. Grow more crops to keep pace with a growing population, and the humidity, the carbon dioxide balance, and the wastewater treatment load all shift as well. None of these systems can be designed in isolation, which is part of why building a generation ship is closer to designing an entire artificial biosphere than designing a spacecraft. Food deepens the challenge further, because unlike air and water, food cannot simply be cleaned and reused. It has to be grown, generation after generation, inside a structure that will never again receive a shipment of seeds, fertilizer, or replacement livestock from anywhere. Whatever biological diversity leaves Earth at departure is, for practical purposes, all the biological diversity that will ever exist for that voyage. A handful of unlucky crop diseases, left unchecked, could wipe out a species of grain that an entire population depends on for calories, with no fresh stock anywhere in the universe to replace it. This is why serious designs for such ships treat their onboard farms less like gardens and more like insurance policies. Multiple varieties of each staple crop would likely be grown in parallel, in separate sealed compartments, so that a disease or pest outbreak in one area cannot spread to wipe out the entire food supply at once. Seed banks would be kept in cold, stable storage, untouched for years, ready to restart a crop line if an active planting ever failed. Even livestock, if any is carried at all, would need enough genetic variety among a small number of animals to avoid the slow, grinding problems that come from breeding too few individuals together over too many generations. Every one of these safeguards costs space, costs mass, and costs constant attention from people whose entire lives will be spent tending crops they may never taste in ideal form, on a ship built by ancestors they never met, heading toward a destination they will never personally reach. Medicine faces a version of the same isolation, though the danger here is quieter and slower to appear. On Earth, a doctor treating an unusual illness can eventually draw on knowledge gathered from billions of people, decades of research, and a constant stream of new treatments developed somewhere else on the planet and shared almost instantly. Aboard a ship sealed off from that entire body of ongoing discovery, medicine effectively freezes at the moment of departure, supplemented only by whatever the population manages to learn on its own along the way. Any medical library carried aboard would need to be extraordinarily thorough, covering not just common illnesses but rare conditions, surgical procedures, and treatments that a small population might otherwise never encounter in enough numbers to justify carrying detailed instructions for. Training would need to be spread widely rather than concentrated in a few specialists, for the same reason that every other critical skill needs redundancy, because losing the only person who understood a particular procedure could mean losing that capability entirely for everyone who comes after. There is also a subtler concern that has nothing to do with accidents or emergencies. A sealed population carries its own bacteria, its own viruses, and its own quiet biological history along with it, isolated from the constant churn of new exposures that a planet's full population experiences. Over enough generations, the balance between people and the microorganisms living alongside them can shift in unpredictable ways, sometimes toward a kind of stability, and sometimes toward new vulnerabilities that nobody could have tested for in advance, since there has never before been a human population living in quite this kind of total, sustained isolation. Genetic health adds one more layer to this picture. Beyond simply keeping the founding population large enough to avoid inbreeding, random mutations occur constantly in every generation, most harmless, occasionally beneficial, and occasionally troubling. On Earth, A harmful mutation is usually diluted across a vast, constantly mixing population. Aboard a smaller, closed community, careful record-keeping and thoughtful family planning across generations would likely become an ordinary part of life, not out of any desire to control people's choices, but simply as a practical extension of the same redundancy and care applied to every other fragile system aboard. None of this makes the population a laboratory experiment, and it would be a mistake to think of it that way. It simply means that health, like air and water, becomes something actively managed and quietly tracked for the entire length of the voyage, generation after generation, by people whose job is to notice slow trends long before they become emergencies. That kind of quiet, ongoing vigilance would likely become one of the most valued and most invisible forms of work aboard the entire ship, unnoticed on any single ordinary day, yet directly responsible for making sure that ordinary days keep arriving, one after another, for as long as the voyage lasts. Step back far enough, and the ship stops looking like a vehicle at all, and starts looking like an ark in the oldest sense of that word. A single vessel carrying a small, carefully chosen sample of everything a living world normally provides in overwhelming abundance. Earth holds millions of species, countless strains of crops and livestock, and an almost uncountable diversity of microorganisms quietly supporting every larger form of life above them. A ship can carry only a tiny fraction of that, a deliberate, curated selection chosen specifically for how well each organism supports human survival and how resilient each one proves to be under sealed, artificial conditions far removed from the wild, chaotic abundance of an actual planet. Every choice about what to include, and just as importantly what to leave behind, becomes an enormous responsibility placed on whichever group of scientists and planners assembles the ship's original biological cargo. This selection process would likely stretch across years of careful debate long before the ship ever launches, weighing every candidate organism not just for its usefulness, but for how well it tolerates confinement, artificial light, altered gravity, and the complete absence of the wider ecological web it would normally exist within on an actual planet. Some organisms that thrive easily on Earth might prove surprisingly difficult to sustain aboard a sealed ship, while others considered minor or unremarkable back home might turn out to be unexpectedly vital once the full web of dependencies inside the hull becomes clear. A soil bacterium here, an insect there, quietly holding together a chain of function nobody fully appreciated until it was needed. Leave out a particular strain of beneficial soil bacteria, and the crops relying on it years into the voyage might struggle in ways nobody predicted at launch, with no way to acquire a replacement. Include too narrow a selection of pollinating insects, or skip them because they seem inconvenient to manage aboard a sealed hull, and entire categories of crops that depend on them might quietly fail decades later, for reasons that trace back to a single decision made before the ship ever left the ground. The same weight applies to human culture and knowledge, carried not as biology but as memory. Every book, every piece of music, every recorded skill and historical account that leaves Earth aboard that ship becomes, in a very real sense, permanent, since there is no library elsewhere to consult if something important was accidentally left out. A civilization's entire accumulated understanding of medicine, engineering, agriculture, and history has to be compressed into an archive thorough enough to answer questions that have not even been asked yet, questions that might only arise 5 or 6 generations into the voyage, long after anyone who could have gone back to check with Earth is gone. Redundant copies of that archive would need to be stored in multiple physically separate locations throughout the ship, protected against the same fires, floods, or system failures that any other critical resource aboard has to be protected against, since losing the only copy of a crucial piece of accumulated human knowledge would be every bit as damaging as losing the only crop of a staple grain. Deciding how that archive should be organized carries its own quiet responsibility as well. Since a library that is merely enormous does no good if nobody generations later can find the specific piece of information they urgently need. Clear indexing, redundant formats, and simple, durable languages for critical instructions would likely matter as much as the sheer volume of material stored, since an archive nobody can navigate under pressure is barely better than no archive at all. This is why some who study these proposals describe the entire vessel less as a spacecraft and more as a seed, a single, dense package carrying the minimum necessary pattern of an entire civilization, launched outward with the hope that it can unfold into something whole again once it finally reaches soil capable of supporting it. There is a strange comfort hidden inside how unprecedented this all sounds, because in a narrower sense, humanity has attempted something like it before. Long voyages across open ocean, carried out over history by different peoples in different parts of the world, using nothing more advanced than sail, current, and memory. Sometimes lasted long enough that entire journeys were planned around the knowledge that not everyone aboard would necessarily see land again personally, and that the true payoff of the voyage might belong more to descendants than to the travelers themselves. Those crossings were nowhere near as long as centuries, and the ocean, however dangerous, was never as absolute or as unforgiving as the vacuum between stars. But the underlying shape of the challenge rhymes across an enormous gap in time and scale. A small, sealed group of people, carrying a condensed version of everything their culture considered essential, setting out toward a horizon they could not fully verify in advance, trusting careful preparation and hard-won knowledge over blind hope. A generation ship simply removes every safety net those earlier voyages still quietly relied upon. No coastline to turn back toward, no possibility of favorable winds shortening the trip, no chance encounter with another vessel offering unexpected help along the way. It keeps only the core of the old challenge and multiplies its duration by many hundreds of times, asking an entire small civilization to do deliberately over centuries, and with total isolation, what smaller groups once did across single lifetimes, with at least some hope of solid ground still somewhere within reach. Beyond crops and beneficial microorganisms, most serious proposals also give real thought to whether the ship should carry animals purely for companionship rather than for food or ecological function. A population living for centuries inside a sealed structure, however well designed, would likely benefit from something as simple as the presence of a dog curled up by a doorway, or a cat stretched out along a warm pipe. Small, familiar reminders of a kind of life that has nothing directly to do with survival systems or resource management. The practical cost of carrying such animals is real, since every living creature aboard consumes food, water, and space that could otherwise support the human population or its agricultural systems, and every species carried has to be genetically diverse enough within the small numbers available to avoid the exact same long-term health problems facing the human population itself. Some proposals suggest limiting companion animals to a small number of hardy, well-understood species, chosen deliberately for how little additional strain they place on the ship's closed-loop systems, rather than attempting to recreate the full range of pets familiar from Earth. Whatever the final decision, the underlying reasoning tends to be the same reasoning applied to art, music, and open sightlines throughout the ship, an acknowledgement that keeping a population healthy for centuries requires more than simply keeping their bodies alive, and that some of the smallest, least essential seeming comforts may do quiet, essential work in keeping an entire closed society emotionally stable across generations who will never know any other kind of home. Light for the ship's crops presents its own separate puzzle, because for most of an interstellar crossing, there is no nearby sun bright enough to grow anything. An orbiting habitat close to Earth can use mirrors to redirect genuine sunlight into its growing areas, essentially borrowing daylight from a star that is already doing all the hard work. A ship traveling between stars spends the overwhelming majority of its journey in the dark gap between them, where the light from both the departure star and the destination star has faded to something closer to a distant, dim point than a source of usable energy. That means the crops, the lighting, the heating, and every machine aboard have to run on power generated internally, carried along for the entire journey rather than harvested along the way. This almost certainly means some form of nuclear power, likely a design intended to run reliably and safely for the full length of the voyage without needing refueling from outside sources. It might mean fission reactors built with enormous safety margins, or a more advanced form of nuclear power still years from being proven at this scale. Either way, the ship becomes something like a small, self-contained power station wrapped around a small, self-contained farm, wrapped around a small, self-contained ocean and atmosphere, wrapped around a small, self-contained society, with no external grid, no external supply chain, and no external sun to rely on for most of the trip. Either way, the ship becomes something like a small, self-contained power station wrapped around a small, self-contained farm, wrapped around a small, self-contained ocean and atmosphere, wrapped around a small, self-contained society, with no external grid, no external supply chain, and no external sun to rely on for most of the trip. Whatever reactor design is chosen, it would almost certainly need to be built with several complete backup units, rather than relying on a single power source for the entire voyage. Since losing all electrical power aboard a sealed ship would very quickly become catastrophic, halting air, recycling, water treatment, and crop lighting all at once within a matter of hours rather than days. Engineers would likely also want the reactors positioned with enough physical separation that a single serious accident affecting one unit could not easily damage its neighbors, echoing the same redundant, compartmentalized thinking that shapes nearly every other critical system aboard. Only in the final stretch, as the ship begins its long deceleration toward the destination star, does natural starlight return as a meaningful presence again, and by then, the population aboard will likely be many generations removed from anyone who ever grew a single crop under real, unfiltered sunlight. Speed brings its own kind of danger, one that has nothing to do with running out of food or air. Interstellar space looks empty on a map, but it is never perfectly empty. Thin clouds of gas and scattered dust drift between the stars, along with a steady rain of charged particles moving in every direction. At ordinary planetary speeds, none of this matters much. A ship traveling toward another star, however, would likely need to move at a meaningful fraction of the speed of light simply to complete the journey within a survivable number of generations. And at those speeds, even a single tiny grain of interstellar dust becomes something closer to a bullet. A particle smaller than a grain of sand, struck at a large enough fraction of light speed, carries an amount of energy far out of proportion to its size, more than enough to punch through a hull wall if the shielding in front of it is not thick enough or angled correctly. The faster the ship travels, the more violently even the faintest specks of matter in its path arrive. Some proposed designs address this with a forward shield, a thick barrier of ice, water, or dense material mounted at the front of the ship, absorbing impacts before they ever reach the areas where people live. Water is an especially attractive choice, since the same mass that blocks incoming particles can later be melted down and folded back into the ship's water supply once the ship has slowed enough that the danger has passed. Radiation from deep space adds a second layer to the same problem. Without a planet's thick atmosphere and magnetic field standing guard the way Earth's does, a ship in open space receives a steady dose of high-energy particles streaming from stars, from the wreckage of ancient supernovae, and from sources scattered across the galaxy. Over a journey lasting mere months, this exposure is manageable. Over a journey lasting centuries, it becomes one of the defining hazards of the entire voyage, capable of raising long-term health risks for everyone aboard, if the shielding is not taken seriously from the very beginning. Engineers studying this problem often describe it less in terms of the size of the incoming particle and more in terms of the energy it carries at the moment of impact, since a piece of dust weighing almost nothing can still release a burst of heat and pressure large enough to vaporize a small area of hull material on contact if the ship is moving fast enough when the collision happens. A forward shield, whether built from layered ice, compacted material, or something more exotic, works by breaking that single violent impact into something more manageable, vaporizing the incoming particle across a wide, expendable outer layer, rather than allowing its full energy to strike a single, small point on the ship's actual living structure. Ice offers a particularly attractive option for this outer layer, since it is relatively easy to shape, can be replenished slowly from the ship's own water reserves, if it erodes over the centuries of travel, and provides meaningful protection against both incoming dust and background radiation at once, doing two jobs with a single, relatively simple material rather than requiring separate, more complex shielding systems for each threat. The trade-off, as with everything else aboard, comes down to mass, since a shield thick enough to handle centuries of accumulated impacts adds enormous weight to the front of the ship, weight that then has to be accelerated and decelerated along with everything else, which is part of why some designs favor slightly thinner shielding paired with active monitoring and course correction, rather than relying on sheer bulk alone to guarantee safety. Sensors and tracking systems built into the leading edge of the ship would also likely play a role, watching for larger fragments early enough that minor course corrections could nudge the ship out of their path entirely, reserving the heavy shielding for the countless smaller particles too numerous and too faint to track individually. This is why the living areas of such a ship would likely sit deep inside the structure, surrounded by water tanks, stored supplies, soil, and other dense material doing double duty as both storage and armor. Nothing wasted, nothing purely decorative, every wall doing at least two jobs at once. The hull itself carries a burden that rarely gets discussed outside of engineering papers, and it deserves more attention than it usually receives. Metal, ceramic, and composite materials do not remain perfectly stable forever, even sitting quietly on a shelf, and they certainly do not remain perfectly stable while enduring centuries of temperature changes, vibration from machinery, and the constant faint stress of internal pressure pushing outward against the vacuum beyond the walls. Materials fatigue over time, developing microscopic cracks that slowly grow with every cycle of stress. Whether that stress comes from a temperature shift, a change in acceleration, or simply the passage of enough years. On Earth, a bridge or a building can be inspected regularly and rebuilt entirely once it approaches the end of its useful life, using fresh materials brought in from elsewhere. A ship traveling between stars has no elsewhere to bring materials from, which means its structure has to be either wildly overbuilt from the very beginning, carrying far more strength than any single moment actually requires, or continuously monitored and repaired using onboard manufacturing capable of replacing sections of hull long before they ever become dangerous. Both approaches are almost certainly needed together. Sensors embedded throughout the structure would need to track stress and strain constantly, watching for the earliest signs of fatigue long before a human inspector could notice anything by eye. While teams trained specifically in structural maintenance would need to treat hull integrity as an ongoing, permanent project rather than a problem solved once at launch and then forgotten. This is one more example of the same underlying pattern running through every part of the ship. Nothing gets built once and left alone. Everything is watched, maintained, and slowly renewed, generation after generation, by people whose entire working lives may be spent caring for a structure that will still need care long after they are gone. Some sections of hull would likely be designed from the outset to be fully replaceable, built-in modular segments that can be swapped out entirely rather than repaired in place, treating certain parts of the ship less like permanent architecture and more like components in an enormous, slow rotating inventory. Each one eventually cycled out, reprocessed, and rebuilt from its own reclaimed material before fatigue ever becomes a genuine danger. This kind of planned, rolling renewal changes how residents might think about their own home in a subtle but important way. Since a wall or a section of floor is never truly permanent, understood from birth to be something that will eventually be dismantled and rebuilt long before it fails, rather than something expected to last forever untouched. That expectation would likely shape an entire cultural attitude toward permanence and change, one quite different from how most people on Earth tend to think about their own homes, since a resident aboard the ship grows up knowing that even the walls around them are part of an ongoing cycle of careful renewal rather than a fixed, unchanging backdrop to their life. Gravity, or rather its absence, shapes the ship just as forcefully. Long-term weightlessness slowly weakens bone density and muscle mass, changes fluid distribution throughout the body, and creates health complications that become more serious the longer they continue unaddressed. A crew enduring weightlessness for a few months can recover afterward through careful rehabilitation once they return to solid ground. A population living without gravity for generations has no such return trip to look forward to. And children born and raised in true weightlessness might develop very differently from their ancestors in ways that current medicine still cannot fully predict. The most straightforward answer is rotation, the same basic trick used by orbiting habitats near Earth. Spin some portion of the ship, whether the entire vessel or a dedicated ring built around its structure, and the people inside experience something that feels close enough to true gravity for their bodies to function normally. Feet press against floors. Water pours the way it should. Bones and muscles keep the loads they were built to carry. But a spinning ship, traveling at a meaningful fraction of light speed, introduces engineering complications that a stationary orbital habitat never has to consider. The spinning section has to remain balanced and stable even as the ship accelerates, decelerates, and adjusts its heading over centuries of travel. Any asymmetry in mass distribution, caused by shifting supplies, growing crops, or a population that is not spread perfectly evenly through the structure, has to be constantly corrected, or the entire ship risks a wobble that no one aboard would want to experience at those speeds. The rotating sections would also need to interact carefully with the ship's radiation shielding and its propulsion systems, since a design that works beautifully for comfort might create weak points in protection, and a design that maximizes protection might make comfortable rotation far more difficult to achieve. Every choice made for one system quietly reshapes what is possible for the others, which is really the entire theme running underneath a project like this. There is no piece of the ship that exists on its own. Rotation alone would be a manageable engineering problem if the ship simply drifted at a constant speed for its entire journey, since a spinning ring behaves predictably once it settles into a steady rate of turn. The complication arrives whenever the ship needs to change its motion, firing engines to accelerate at the start of the voyage, adjusting course along the way, or decelerating hard as it finally approaches its destination. A spinning section reacts to those forces, the way a spinning top reacts to being pushed sideways, resisting the change in ways that are not always intuitive, sometimes twisting or tilting rather than simply speeding up or slowing down in a straight line. Engineers studying these designs generally conclude that major thrust maneuvers would need to happen either with the rotating sections temporarily slowed or stopped, or with the entire ship's structure engineered specifically to tolerate the combined stress of spinning and accelerating at the same time. Neither option is simple. Stopping the rotation means the population briefly loses the gravity they depend on for comfort and health precisely during the most demanding and important maneuvers of the entire voyage, the initial acceleration and the final approach. Building a structure tough enough to spin and accelerate simultaneously means carrying additional structural mass, specifically to survive combined forces that a stationary structure would never need to withstand at all. Most serious proposals lean toward long, gentle periods of acceleration and deceleration precisely because of this tension, spreading the change in speed across months or years rather than compressing it into a short, violent burn, allowing the rotating sections to adjust gradually rather than being wrenched suddenly out of their steady spin. Perhaps the least visible constraint of all, and arguably the most unforgiving, is the population itself. A ship can carry excellent engineering and still fail because of biology, specifically the biology of maintaining a healthy, genetically diverse human population across many generations with absolutely no fresh arrivals from outside. Population geneticists who have studied this question generally suggest that a starting population numbering in the low thousands, and quite possibly needing to be considerably larger, would be necessary to avoid the slow accumulation of genetic problems that come from too small a gene pool breeding within itself for centuries. Go too small, and generations down the line begin to see the same inherited conditions appearing again. The quiet cost of a founding population that looked adequate on a spreadsheet but proved too narrow in practice. Small, isolated human populations on Earth, cut off for long stretches on remote islands or in extremely secluded valleys, have occasionally shown exactly this pattern across only a handful of generations. Certain inherited conditions becoming unusually common simply because the pool of ancestors everyone descended from was too narrow to begin with. A generation ship faces an even harsher version of that same risk, since an island population can eventually be refreshed by new arrivals from elsewhere, while a ship population, sealed for centuries with no possibility of new arrivals at all, has to get the founding numbers right on the very first attempt, with no opportunity to correct course once the hull doors have closed. This single requirement, more than almost any other, sets the minimum size of the entire ship. Once you commit to keeping several thousand people healthy across many generations, you are no longer designing a small exploratory capsule. You are designing a floating town, complete with homes, schools, clinics, farms, workshops, and every ordinary structure a small society actually needs to keep functioning, all wrapped inside a hull, built to survive both the vacuum outside and the slow demands of human genetics within. A town that size needs rules, and rules aboard a sealed ship carry a weight they rarely carry on Earth. On a planet, someone who disagrees strongly enough with their community can leave, move to another town, another country, another way of living entirely. That option simply does not exist inside a hull traveling between stars. Every disagreement, every conflict, every difference of opinion about how resources should be shared has to be resolved by people who will still be living beside each other tomorrow, next year, and likely for the rest of their lives, with no possibility of quietly walking away. This changes what kind of governance actually works. A system that concentrates too much power in too few hands becomes dangerous quickly, since there is no outside authority to appeal to and no election on a distant continent that might eventually correct course. Many serious proposals for long-duration voyages favor deliberately distributed authority instead, with responsibilities rotated regularly among trained groups, and with critical decisions, particularly anything touching food allocation, medical priorities, or population planning, made through processes designed specifically to resist being captured by any single family or faction over the long run. Imagine a disagreement several generations into the voyage over how much of the remaining stored water reserve should be released to expand a struggling section of farmland versus held back as emergency insurance against a future equipment failure. On Earth, such a dispute might be settled by importing more water, or simply waiting for the next rainy season to resolve the shortage naturally. Aboard the ship, there is no rain to wait for and no import to arrange, which means the disagreement has to be settled entirely through whatever governance structure the ship has built for exactly this purpose, weighing the farm's real need against the genuine risk of leaving less in reserve, with every resident aware that the decision, once made, cannot easily be undone or supplemented from outside. This is the kind of dispute a sealed, resource-limited society would face constantly and quietly, not through dramatic confrontation, but through careful, repeated negotiation over genuinely scarce and irreplaceable resources, decided by people who know they will still be sharing meals with whoever disagreed with them long after the matter is settled. Legal and social customs would also likely need to evolve gradually, rather than staying frozen at the moment of departure. Governance would also eventually need some way of handling a possibility that founders might prefer not to think about too closely: the chance that a later generation, having never chosen this voyage themselves, comes to genuinely question whether continuing toward the original destination remains the right decision at all. A population several generations removed from Earth, having built an entire functioning society inside the ship itself, might reasonably ask whether the original goal still deserves the same authority it once held, particularly if updated information suggests the destination is less promising than once believed, or if the ship's own internal society has become something its residents value deeply in its own right. Serious proposals generally suggest that some structured, legitimate process for revisiting the mission's fundamental goals needs to be built into the ship's governance from the very beginning, rather than leaving such a fundamental disagreement to be settled only through informal pressure or unofficial rebellion, since a closed population with no way to physically separate from one another cannot afford to let a disagreement that deep go unresolved or unacknowledged. This does not mean the original mission would be abandoned lightly. Most proposals imagine any such review requiring broad, deliberate consensus reached over a long period of open discussion, precisely to prevent a passing mood, a difficult year, or a small vocal group from overturning a goal that centuries of prior residents worked and sacrificed to sustain. The point of building this process into the ship's governance from the start is not to make abandoning the mission easy, but to make sure that if doubt ever does become widespread and genuine, it has a legitimate, peaceful path to be heard and addressed, rather than curdling quietly for generations into resentment, secrecy, or eventual conflict within a population that has nowhere else to direct that frustration. Laws written by the founding generation, however carefully considered, are unlikely to remain perfectly suited to a society 5 or 6 generations removed from anyone who actually experienced life on Earth. The ship would need some accepted way of updating its own rules over time, a kind of living constitution capable of change, while still protecting the handful of absolute priorities, keeping the air breathable, the water clean, and the population healthy, that can never be allowed to become negotiable no matter how governance evolves around them. Language and culture drift in their own quiet direction as well, and this may be one of the most fascinating consequences of the entire journey. Isolated populations on Earth, even ones separated by nothing more than a stretch of ocean or a mountain range, tend to develop their own accents, their own turns of phrase, their own customs, within a surprisingly small number of generations. A population sealed for centuries inside a single ship, with no outside contact reshaping its speech or habits, would very likely develop something recognizably its own, a dialect, and eventually perhaps a language that the ship's founders would find only partly familiar if they could somehow hear it. Earth itself would undergo the same transformation in reverse. The culture, technology, and even the political map that existed at departure would continue changing back on the home planet for as long as the ship traveled, meaning that any archived recordings of Earth carried aboard would grow more historical, more distant, and more curious with every passing generation, a fixed snapshot of a world that never stopped moving without them. Traditions would form aboard the ship that had nothing to do with Earth at all. Anniversaries tied to events that happened only within the hull. Songs written by people who had never seen rain. Stories about the great-grandparents who remembered the true sky, told the way people on Earth once told stories about ancestors who crossed oceans in wooden ships, not knowing exactly what waited on the other side. Even something as basic as keeping track of time would need to be reconsidered from the ground up. On Earth, a day is simply what happens while the planet completes one full turn, and a year is what happens while it completes one full orbit around the sun, both anchored to something physical and unmistakable that everyone can see for themselves. Aboard a ship traveling through the dark gap between stars, with no meaningful sunrise for most of the journey, the length of a day becomes an entirely artificial choice, set by whoever designs the lighting schedule rather than dictated by any nearby star. Most proposals assume the ship would keep something close to the familiar rhythm humanity evolved with, a day and a year modeled deliberately on Earth's own cycle, chosen specifically because human bodies and minds already respond well to that particular rhythm of light and rest. But that choice is a decision, not a natural fact, made consciously by the ship's original designers and then inherited, unquestioned, by every generation that follows, few of whom would ever think to ask why a day lasts exactly as long as it does when there is no sun outside dictating the answer. Marking the passage of years would carry its own quiet strangeness as well. A calendar aboard the ship would need to track not just days and years, but generations, milestones, and the ship's own internal history, since the usual markers people use to place themselves in time, a particular season, a familiar constellation, current events happening elsewhere, simply would not exist in the same way. Time aboard the ship would likely come to be measured less by the position of any star and more by the ship's own internal story. The year a particular reactor was overhauled, the generation that first proposed a new law, the anniversary of departure itself, celebrated further and further from the world it once meant, until it becomes less a memory and more a founding myth. All of this engineering exists in service of something harder to design for than any pump or reactor, which is the fact that almost everyone aboard will spend their entire life on a ship they never chose to board. The people who make the decision to launch will not be the people who arrive. Their children and their children's children, and many generations after that, will be born already in transit, will grow up already in transit, and will end their days still in transit, having inherited a destination rather than selected one for themselves. Imagine explaining to a child why the walls curve the way they do, why the sky above their head is a ceiling filled with lights that dim on a schedule instead of a true sun that rises and sets on its own, why their entire world is smaller than a single neighborhood back on the planet their great-grandparents left behind. For that child, none of this will feel strange, in the same way that a fish does not experience water as unusual. The ship simply is the world, and the concept of an open horizon, a real ocean, or weather that arrives without anyone scheduling it, will exist only as a story told by adults about a place none of the children have ever seen. That raises a genuinely difficult question that no amount of clever engineering can fully answer. How do you keep an entire population motivated toward a shared goal across so many generations that the goal itself becomes an inherited idea rather than a personal memory? The first generation aboard will remember Earth directly. The second generation will remember hearing about it from parents who remembered it directly. By the fifth or sixth generation, Earth becomes something closer to a distant legend, technically true, endlessly documented, but emotionally as remote as any historical event feels to people living centuries after it happened. Meanwhile, the destination remains just as distant in the other direction, a future promise rather than a present reality, something that will matter enormously to a generation not yet born. This creates a strange emotional inheritance passed down through the ship's entire history, a purpose everyone is asked to hold on to, even though almost nobody currently alive will ever personally see it fulfilled. This creates a strange emotional inheritance passed down through the ship's entire history, a purpose everyone is asked to hold on to, even though almost nobody currently alive will ever personally see it fulfilled. That gap would likely be felt most sharply between the very first generation, who remember Earth directly and chose this life deliberately, and the second generation, born aboard, who inherit both the mission and the homesickness of their parents without ever having anything of their own to be homesick for. Some who study these proposals suggest this transition between the first and second generations may actually be the single most psychologically difficult period in the ship's entire history, harder even than the isolation faced by later generations who never knew anything different. The first generation carries grief for a world they chose to leave, while quietly raising children who will never share that grief and may instead grow up slightly puzzled by parents who sometimes seem to be mourning a sky, an ocean, or a season that the children themselves have only ever encountered as description rather than memory. By the third or fourth generation, this tension tends to resolve on its own, simply because nobody remaining aboard carries any personal memory of Earth to feel homesick for, and the ship itself has fully become, for everyone living, the only home that has ever mattered. Loss would need its own careful place within this closed community as well, handled with particular thought given how small and tightly bound the population would remain across the entire voyage. When someone aboard eventually grows old and passes on, or is lost earlier through accident or illness, the community loses not just a person but, in a very real sense, a fraction of its already limited store of experience and skill, which means grief aboard the ship would likely be treated as both a deeply personal matter and a genuine community concern, marked with real ceremony rather than something handled quietly and moved past. Remains would most likely be returned to the ship's own material cycle in some form, whether through careful composting that eventually supports the very crops feeding the community, or through methods that convert the body into material the ship can use again. An idea that might sound unsettling described plainly, but one that residents raised entirely within a culture built around circulation and reuse might come to regard as a final, fitting contribution rather than anything troubling. Every name would likely be recorded carefully within the ship's own growing history. Since a community this size, with no possibility of ever growing through outside arrival, tends to remember its own dead with particular care, precisely because each person who has been part of the voyage represents an irreplaceable thread in a story that stretches back to a planet fewer and fewer residents will ever have any personal memory of at all. Some who study these questions suggest that meaning aboard such a ship would need to shift gradually away from the distant destination and toward the ship's own ongoing story. The harvest this season, a repair completed successfully, a child raised well, so that daily life does not depend entirely on an arrival that remains, for most residents, a matter of faith rather than direct experience. Childhood itself would look strange to anyone arriving from Earth, though it would feel completely ordinary to the children living it. A child born aboard would learn to walk on a floor that curves upward in the distance, would learn early which areas of the ship carry full weight and which areas near the center feel lighter, and would absorb the ship's daily rhythms of light and dark as naturally as any child on Earth absorbs the rising and setting of the sun. Schools would need to teach far more than the usual subjects, since every child aboard is, in a sense, being trained as a future caretaker of the systems, keeping everyone alive. Basic literacy in how the air recycling works, how the water loop functions, and why certain resources can never be wasted would likely become as fundamental to a ship child's education as reading and arithmetic. Not as specialized technical training reserved for a few, but as common knowledge every resident is expected to carry. Physical education would need to look different as well, since children raised partly under full simulated gravity and partly, during visits toward the ship's center, under conditions closer to weightlessness, would need careful guidance to keep their growing bodies strong and properly developed in both settings. A child who spent too much time in the lighter gravity regions during critical years of bone and muscle development might grow up with a body poorly suited to a lifetime spent mostly under full simulated weight, which is one more reason daily routines and school schedules would likely be built around ensuring every child spent enough time in the ring itself, regardless of how appealing the near weightless play areas near the center might seem to them. Regular medical monitoring throughout childhood would likely track bone density, muscle development, and balance far more closely than routine checkups on Earth ever need to, catching any early sign that a particular child's body was not adapting well to the ship's artificial gravity before that issue became a lasting health concern rather than something easily corrected with adjusted routines. Family planning would carry a weight aboard the ship that it rarely carries on a planet with room to spare, because the population has to stay within a fairly narrow range to match the ship's fixed life support capacity. And because genetic diversity has to be actively protected across generations rather than left to chance, decisions about when and how many children are born would likely involve community-level planning in a way that feels intrusive by Earth standards, but would be treated aboard the ship as simply another form of the same careful resource management applied to water, food. None of this need be handled harshly or coldly. It would more likely become an accepted, unremarkable part of life, discussed openly and taught to each new generation the same way children on Earth are taught why clean water matters or why forests need protecting, not as a restriction imposed from outside, but as an inherited responsibility toward everyone still waiting to be born after them. It helps to imagine what a single, ordinary day aboard such a ship might actually feel like, rather than only listing the systems that make it possible. A resident wakes as the overhead lighting shifts gradually from a dim night setting towards something brighter, A sunrise with no sun behind it, timed precisely to match the rhythm their body has known since birth. Breakfast might include bread from grain grown a short walk away and fruit from trees planted by residents who are, by this point, several generations gone, their names remembered mainly because a plaque or a family story still credits them with the orchard. Walking to work might mean passing through a district where the ceiling curves upward into what looks almost like a hazy sky. Farmland stretching along the inner surface of the ring, workers already tending crops under carefully scheduled light. A shift at a water treatment station, a school, a workshop repairing worn machine parts, or a clinic checking on an elderly resident would all feel, to the person doing them, like perfectly unremarkable work. The same way a plumber or a teacher on Earth rarely spends the day marveling at the technology beneath their profession. Lunch might be eaten with neighbors in a shared courtyard, conversation drifting toward local matters, a disagreement over a proposed change to the crop rotation, a rumor about a data packet finally arriving from Earth after decades in transit, a child's exam results, nothing that would sound out of place in any small town anywhere. In the evening, someone might walk along a path bordered by trees, glance upward at a curve of homes and lights on the far side of the ring, and feel nothing more dramatic than the ordinary comfort of being somewhere familiar as the artificial day fades toward artificial night. None of this would feel, to the people living it, like survival. It would simply feel like life, precisely because every system described so far, the air, the water, the food, the shielding, the gravity, has done its job well enough to fade into the background, leaving room for something as small and human as a shared meal or a walk at the end of the day. That, more than any single piece of hardware, is the actual measure of whether a ship like this has succeeded. Motivation alone cannot carry a closed population through centuries of confinement, which is why serious proposals spend almost as much thought on daily comfort and mental well-being as they spend on air and food. A population that never sees anything resembling open space, natural light, or genuine variety in its surroundings tends to suffer for it, in ways that show up slowly as restlessness, low mood, and quiet friction between neighbors who have nowhere else to go. This is why many designs devote real structural effort to parks, gardens, and public spaces built with deliberately long sightlines, places where a person can walk far enough to lose sight of the nearest wall, even if they know perfectly well that the wall is only a short distance away. Living plants matter here, beyond their role in producing food and oxygen, since something that grows, changes, and responds to the seasons gives the eye and the mind somewhere to rest that a purely mechanical corridor cannot offer. Art, music, and craft would likely matter more aboard such a ship than almost anywhere on Earth, not as luxuries, but as some of the only truly personal, unscripted activities available to people whose entire physical environment has been engineered down to the smallest detail. A hand-carved object, a song written about nothing more than the way morning light moves across a particular wall, a mural painted by a child who has never seen the ocean it depicts. All of it becomes a quiet act of claiming a manufactured world as something personally lived in rather than merely survived. Physical recreation would matter just as much as quiet, reflective spaces. Since a population confined to a fixed structure for its entire life would need genuine outlets for competition, exertion, and simple physical joy, whether through sport adapted to the ship's available space, swimming in shared pools built partly to double as emergency water reserves, or simply running along a long, looping path that lets someone feel, briefly, like they are covering real distance rather than circling the same small world again and again. Celebrations and shared rituals, birthdays, harvest festivals, anniversaries of the ship's own history would likely take on outsized importance as well. since a closed population benefits enormously from regular, predictable moments of shared joy that break up the routine of ordinary life without threatening the underlying schedules everything else depends on. Some of these celebrations would likely blend inherited Earth traditions with entirely new customs born only aboard the ship itself, a holiday reshaped to fit the ship's own artificial seasons, a song passed down but slightly changed in meaning, a story about the voyage's early years told and retold until it becomes something closer to shared folklore than simple historical record, binding generations together through memory, even as the details of Earth itself grow steadily more distant. Designers of these concepts also have to think seriously about education, in ways that have almost nothing to do with rockets. Every generation focuses heavily on education, making sure each new generation understands not just how to operate the ship's systems, but why those systems matter, so that critical knowledge is never lost simply because the people who first understood it have passed on. A ship like this cannot afford to have its most important technical knowledge live only inside a handful of specialists who might, through simple misfortune, be gone before they've had the chance to teach anyone else. Every critical skill needs redundancy in people, the same way every critical system needs redundancy in hardware. It would be reasonable to assume that much of this could simply be handled by automated systems instead, monitoring the ship's air, water, and crops without needing generations of trained people, standing watch over every gauge and readout. Automation would almost certainly handle an enormous share of the ship's routine operation, adjusting lighting schedules, regulating temperature, and managing countless small corrections far faster and more precisely than any human crew could manage manually. But full reliance on automation carries its own quiet danger, one that grows more serious the longer the voyage lasts, rather than less. Software and control systems, like everything else aboard, would need maintenance, updates, and repair across centuries, performed by people who understand not just how to operate the automated systems, but how those systems actually work underneath, well enough to diagnose an unfamiliar failure that no engineer anticipated when the code was first written back on Earth. A population that gradually stopped training anyone to understand the ship's automated systems at a deep level, trusting the machinery completely simply because it had worked reliably for generations, would be quietly setting up its own crisis, one that might only reveal itself the first time something failed, in a way the automation itself was never designed to recognize or correct. This is why most serious proposals treat automation as a powerful assistant rather than a replacement for trained human judgment, insisting that every generation continue producing people who genuinely understand the ship's deepest systems, not merely people who know which button to press when a warning light appears. There is also a subtler argument for keeping humans deeply involved in the ship's operation, one that has less to do with technical failure and more to do with trust. A population that felt entirely disconnected from the systems keeping them alive, dependent on automated processes nobody truly understood anymore, might begin to feel less like residents of their own home and more like passengers aboard someone else's machine, a psychological shift that could quietly erode the sense of ownership and responsibility that seems essential to keeping any closed society functioning well across many generations. This same logic extends into how the ship handles anything that breaks, which brings us to one of the least glamorous but most essential aspects of the entire voyage, the ability to build and repair almost everything using only what is already aboard. It raises a genuinely interesting question of whether a population sealed inside a single ship would keep doing science at all, in the sense of pursuing new discoveries rather than simply maintaining inherited knowledge. Most proposals assume the answer is yes, and that ongoing scientific work would matter more, not less, aboard such a ship, since a population that stopped actively questioning, measuring, and improving its own understanding of the systems, keeping it alive, would be far more vulnerable to a slow decline in competence across generations than one that kept treating its own survival as an active area of study. Observations of the surrounding interstellar environment, the dust, the radiation, the faint light of distant stars, would also give scientifically minded residents something genuinely new to study. Questions that nobody on Earth has ever been positioned to answer firsthand, since no human population before this one has ever traveled far enough to look back at an entire star system from truly deep space. In this sense, the ship would likely remain a working scientific outpost throughout its entire journey, not merely a vessel in transit, quietly gathering knowledge about the space between stars that could eventually be passed back to Earth or carried forward to whatever new world its descendants finally reach. On Earth, and even aboard a station in orbit close to Earth, a broken part can eventually be replaced by ordering a new one and waiting for it to arrive. A generation ship has no supplier to call. Whatever raw materials, tools, and manufacturing capability exist inside the hull at departure are the only raw materials, tools, and manufacturing capability that will ever exist for that voyage, unless the crew finds some way to recycle and reprocess what they already have into something new. This effectively means the ship needs its own small manufacturing base, capable of producing spare parts, replacing worn components, and even fabricating entirely new equipment if an old design turns out to be flawed after decades of use in ways nobody anticipated at launch. Metals would need to be recovered and reused rather than discarded. Plastics and composites would need recycling processes robust enough to run indefinitely without degrading the material beyond usefulness. Even something as simple as a worn seal or a cracked pipe becomes a small crisis if the ship cannot manufacture a replacement because there is no emergency supply drop waiting anywhere nearby. This changes the kind of people such a ship would need to carry. Alongside farmers, doctors, and engineers, a healthy population would need skilled machinists, chemists, and technicians capable of keeping an entire industrial base running with a fixed, finite stock of raw materials for hundreds of years. Modern manufacturing tools that build objects layer by layer from raw feedstock, rather than cutting them from larger blocks of material, would likely play a significant role here, since that approach tends to waste far less raw material than traditional manufacturing, and can be adapted relatively quickly to produce a replacement part that was never anticipated at the time of departure. Even so, every machine used to build replacement parts is itself a machine that will eventually wear out and need replacing, which means the ship would likely need to carry the tools and knowledge required to manufacture its own manufacturing equipment. A strange kind of industrial self-sufficiency that has never really been attempted at this scale before, since even the most remote settlements on Earth have always retained some thin thread of supply back to the wider world. A workshop aboard the ship would need detailed digital records of every component in the entire vessel, precise enough that a technician generations removed from the original engineers could still produce an exact replacement part from raw material alone, without ever having seen the original manufacturing process performed by anyone still living. Beyond digital records alone, hands-on apprenticeship would likely remain essential. Since some manufacturing skills are difficult to fully capture in written instructions or diagrams, the small feel of a tool under just the right pressure, the subtle sound a machine makes just before something goes wrong, knowledge that tends to pass most reliably from an experienced hand guiding a newer one rather than from any document, however thorough. All of this points toward an economy unlike anything that has ever existed on Earth. One where the total amount of matter available never increases, and where growth in the way we normally use that word simply is not possible. Every atom of metal, water, and organic material carried aboard at departure is, for the entire length of the voyage, the complete inventory the ship will ever have. Nothing can be mined from a new source, imported from another region, or purchased from a supplier somewhere else, since there is no somewhere else within reach. This changes what an economy even means in this setting. Instead of measuring wealth in terms of accumulation, a ship's internal economy would likely need to measure success in terms of circulation, how efficiently material moves from use to waste to reuse without ever being permanently lost from the system. A broken tool is not simply replaced by manufacturing a new one from fresh material, since fresh material barely exists. It is repaired, or its components are reclaimed and reshaped into something else entirely, in a continuous, careful cycle that never truly ends. Waste in the ordinary sense, something thrown away and forgotten, becomes almost a foreign concept, since anything discarded still occupies mass that the ship can never recover from outside. Even population growth has to be considered through this lens, since more people require more of everything: air, water, food, and living space, all drawn from the same fixed inventory that arrived at departure. Some proposals suggest the population would need to be deliberately managed within a narrow target range, for this exact reason: not growing freely the way populations do on a planet with room to expand, but held close to whatever number the ship's systems were originally built to support indefinitely. Some proposals suggest the population would need to be deliberately managed within a narrow target range for this exact reason: not growing freely the way populations do on a planet with room to expand, but held close to whatever number the ship's systems were originally built to support indefinitely. Even something as ordinary as clothing falls under this same unforgiving logic, since fabric worn thin cannot simply be replaced with a fresh shipment from elsewhere. Textiles aboard would likely be spun, woven, or otherwise produced from fibers grown specifically for that purpose within the ship's own agricultural system, then mended, patched, and eventually unraveled and respun into something new once a garment finally wears beyond further repair. Following the same circular logic already applied to metal, water, and every other finite resource aboard. A community raised entirely within this kind of economy might come to see a well-mended garment not as a sign of poverty, the way it sometimes is treated on Earth, but as an entirely ordinary, even respected object, valued precisely because someone took the care to keep it useful rather than adding needless new demand to an already carefully balanced system. Communication with Earth adds a final, strange twist to daily life aboard, though it is worth remembering that the strangeness runs in both directions at once. Back on the world the ship left behind, its departure would likely remain a significant historical event for a while, marked by monuments, anniversaries, and generations of schoolchildren learning about the day their planet sent a piece of itself outward toward another star. But Earth, unlike the ship, keeps changing quickly and constantly, its own politics, culture, and daily concerns moving forward, regardless of what is happening light years away inside a sealed hull. Within a few generations, the ship's ongoing journey would likely fade from immediate public attention on Earth, becoming a background fact of history rather than an urgent, closely followed story. Much the same way most people today do not spend their mornings thinking about ships that once crossed oceans centuries ago, however remarkable those crossings once seemed to the people living through them. Occasional updates transmitted back toward Earth, confirming the ship's status and reporting on major events aboard, would likely still be sent as a matter of principle and record-keeping, even once nobody expects an urgent reply. In this sense, The relationship between ship and home planet would slowly transform from an active partnership into something closer to a historical thread, still technically connected, but connected in the way a distant, respected ancestor is connected to descendants who never met them, defined more by inherited memory than by any ongoing exchange. In the earliest years after departure, messages could still travel back and forth in a reasonable amount of time, offering some thin connection to the world the ship left behind. But as the distance grows, that connection stretches thinner and thinner until eventually even light itself, the fastest messenger available, takes years, then decades, to cross the widening gap in either direction. A question sent home might not receive an answer until the person who asked it has grown old, or until they are no longer alive to hear it at all. By the middle of the voyage, meaningful two-way conversation with Earth effectively stops making sense. Any message that does arrive would be describing a world that has already moved on by the time it's received, discussing events, people, and concerns that feel distant and outdated the moment they finally reach the ship. Whatever news does eventually arrive would carry a strange emotional weight once the crew understands what it actually represents. A message celebrating some achievement back on Earth might reach the ship decades after the event it describes, meaning that whatever was being celebrated has already long since faded into ordinary history for everyone back home. While for the ship's population, hearing it for the first time, it might feel like genuine, current news. Grief works the same way in reverse. A message announcing that someone significant to the ship's history is gone might arrive so long after the fact that an entire new generation aboard has already grown up treating that person's earlier messages as living correspondence, only to learn, all at once, that the person behind those words has been gone for years by the time the news physically reaches them. At some point, most of these projects assume that the ship stops treating Earth as a living conversation partner and starts treating it more like an archive, a library of recorded knowledge, culture, and history to be studied rather than a place still capable of responding. The ship becomes truly alone in a way that few human communities in recorded history ever have been, cut off not by distance measured in kilometers, but by distance measured in the true passage of time itself. Every safeguard described so far, the redundant farms, the duplicated medical training, the spare manufacturing capacity, the extra shielding mass, shares one quiet cost that ties the entire project together, and that cost is simply mass. Every additional kilogram carried aboard, whether it is water for shielding, soil for farming, or spare metal for future repairs, has to be accelerated up to the ship's cruising speed at launch, and later decelerated again near arrival. And both of those maneuvers require energy in direct proportion to how heavy the ship has become. This creates a genuine tension at the heart of every design decision. More redundancy makes the ship safer, but a heavier ship is slower to accelerate, slower to decelerate, and demands a far larger and more complex propulsion system to move it all. A designer cannot simply keep adding backup systems without limit, since at some point the added mass makes the entire mission slower or less achievable than a leaner ship carrying somewhat less insurance against failure. This is why so much of the engineering behind these proposals is really an exercise in careful trade-offs rather than simple maximization. Every gram of shielding has to justify itself against the energy cost of carrying it. Every duplicate system has to be weighed against the possibility that the mass spent on it might have been better used doubling up on something else instead. There is no version of this ship that is simply uncomplicatedly safe. There is only a version that has made its compromises as thoughtfully as possible, accepting certain risks deliberately in order to keep other, more critical risks as small as they can possibly be made. preparing an entire population to handle emergencies without any outside help arriving ever would likely make regular drills and training exercises a normal, expected part of life aboard. In much the same way fire drills or emergency procedures already exist in schools and workplaces on Earth, only carried out with far greater seriousness and far greater frequency. Every resident, not merely designated specialists, would likely need genuine hands-on familiarity with basic emergency response, sealing a breached compartment, treating common injuries, or safely shutting down a malfunctioning system, since a real emergency aboard a sealed ship could occur anywhere, at any hour, and might require immediate action from whoever happens to be nearby, rather than waiting for a trained specialist to arrive from elsewhere. Children would likely grow up practicing these drills as an ordinary part of school life, the same way children on Earth practice fire evacuations without much sense of alarm, absorbing serious survival knowledge through repetition long before they are old enough to fully appreciate why it matters. This constant, quiet rehearsal of worst-case scenarios might sound grim, described from the outside, yet it would likely feel, from within the ship's own culture, like nothing more than sensible preparation, one more unremarkable thread woven into the ordinary fabric of growing up somewhere that simply cannot afford to be caught unprepared. One response to this tension appears repeatedly across serious proposals, and it has nothing to do with making any single ship more clever, and everything to do with simple numbers. Rather than committing an entire attempt to reach another star to one single vessel, several designs suggest launching more than one ship at once, either together or spread out over a period of years, each carrying its own independent population and its own complete set of systems. The logic behind this is almost disappointingly simple. A single ship, however carefully engineered, remains a single point of failure for the entire endeavor, vulnerable to one unlucky collision, one uncontainable disease, or one cascading systems failure that no amount of clever redundancy inside that one hull can fully rule out over centuries of travel. Two or more independent ships, traveling the same general route but never depending on each other for survival, mean that the failure of one does not have to mean the failure of the entire attempt. Should conditions allow, the ships might even exchange resources briefly if they pass close enough to each other during the voyage, though most proposals assume each vessel needs to remain fully self-sufficient regardless, treating any contact between ships as a fortunate bonus rather than something the mission plan can safely rely on. This approach does not remove risk, since building and launching multiple complete ships multiplies the enormous cost and effort involved rather than dividing it. But it reframes the entire question of survival, shifting it away from asking whether one particular ship can be made perfect and toward asking whether humanity's overall chance of successfully establishing itself around another star can be improved simply by not placing every hope inside a single hull. There is something quietly humbling in that shift of thinking, an acknowledgement that even the most carefully engineered vessel imaginable cannot be guaranteed against every possible failure across so many centuries, and that genuine resilience might come less from perfecting any single design and more from accepting, honestly, that redundancy at the scale of entire ships may matter just as much as redundancy at the scale of a single water pump or air scrubber. All of this leads to the question every serious design study eventually has to sit with, quietly, for a long time. What happens when something goes wrong in the middle of the crossing? Far from any star, with no rescue possible and no help arriving on any timescale that matters. On Earth, even a severe accident usually happens within reach of other people, other resources, another town, another country, another planet's worth of backup. In the deep gap between stars, a serious failure has to be solved, using only what the ship already carries, by people who may never have trained for that exact situation, because the ship's entire library of experience is limited to whatever has already happened once before in its own history. A fire has to be contained using onboard systems alone. A disease outbreak has to be managed with onboard medicine alone, developed and produced from supplies that cannot be restocked. A structural failure has to be repaired with onboard materials alone, by people whose only teachers were the previous generation, who learned from the generation before that, in an unbroken chain stretching back to engineers on Earth who designed systems they knew they would never personally see fail or succeed. This is why redundancy appears again and again throughout every serious proposal for this kind of ship, not as a luxury, but as the entire philosophy holding the project together. Multiple independent life support systems, so that one failure never becomes everyone's crisis. Multiple separate food sources, grown in isolated compartments, so that one bad harvest or one outbreak of crop disease never threatens the whole population's next meal. Multiple trained people for every critical skill, so that losing any single person, however sad that loss may be for those who knew them, never threatens the survival of everyone else aboard. The ship has to be designed less like a single fragile machine and more like an ecosystem, something that can absorb damage in one part without the whole structure failing at once. The same resilience an actual planet has spent billions of years building into itself through sheer redundancy and scale. There remains one possibility that every honest proposal has to acknowledge, even though almost none of them dwell on it for long, which is the chance that the destination chosen so carefully generations earlier turns out, upon closer inspection, to be unsuitable after all. Observations made from Earth, and even observations made by scout probes sent decades ahead of the crewed ship, cannot guarantee perfect certainty about conditions on a world so far away. A promising target might, upon final approach, reveal an atmosphere too thin, a climate too unstable, or some other complication that only becomes clear once instruments aboard the ship itself can study the world up close. Serious planning for this scenario generally arrives at an uncomfortable conclusion. The ship would need enough remaining fuel and resources to continue onward, either toward a secondary candidate world if one exists within reach, or simply to keep traveling while the population reassesses its options, rather than being forced to attempt a landing on a world that clearly cannot support it. This means the mission's fuel and resource budget cannot be planned around the assumption that arrival guarantees success, and has to include a genuine margin for disappointment, an uncomfortable amount of extra mass and energy set aside specifically for the possibility that the entire multi-century journey does not end where anyone expected it to. For the generation actually facing that possibility, the psychological weight would be immense, arriving after centuries of anticipation, only to learn that the promised destination is not what they hoped, and that their own children may need to continue the search their many times great-grandparents began. It is a sobering possibility to plan for, and yet planning for it carefully may be exactly what separates a mission with any real chance of eventual success from one that simply hopes its first guess about a world it has never actually visited turns out to be correct. Some proposals go further still, suggesting that a truly cautious mission plan should treat the original destination less as a guaranteed endpoint and more as a first, best candidate among several, with the ship's course deliberately designed to allow redirection toward a secondary system if updated observations, whether from onboard telescopes or advanced scout probes, suggest a better option exists within reasonable reach. This kind of flexibility costs additional fuel and adds complexity to the ship's overall design, Yet it may be the single most important safeguard against the one failure mode that no amount of engineering aboard the ship itself could ever fully solve. Arriving somewhere that was never truly ready to receive them. Long before any of that becomes real, an entirely different kind of transition has to be managed, one that may prove just as difficult as the outward journey itself. At some point, likely decades before the destination is reached, the ship has to begin turning its enormous forward momentum into a controlled slowdown, using the same enormous amount of energy it once spent accelerating, spent again in reverse. This deceleration phase would likely last years by itself, an entire stretch of the voyage where the ship's engines, having sat mostly idle for centuries beyond the initial acceleration, are relied upon once more to perform flawlessly after generations of quiet operation. The generation living through this phase carries an unusual burden. They will not be the ones who left Earth, and in most designs, they will not be the ones who finally step onto solid ground either. They are the generation asked to prepare everyone else, teaching their children and their children's children what a real planet is actually like. What gravity feels like without a spinning ring providing it artificially, what weather means when nobody has scheduled it, what it might feel like to stand under a sky that has no visible edge. Much of this can only be taught in the abstract, since nobody currently aboard has any personal memory of an actual planetary surface to draw from. Some proposals suggest the ship would begin cultivating small test environments late in the voyage, controlled outdoor spaces built specifically to let a few generations practice living with less structure and more unpredictability before the real arrival, so that the final transition to an actual world does not overwhelm a population that has only ever known the careful predictability of a sealed hull. Even after arrival, the population would not simply walk outside and begin farming a new planet immediately. Whatever world the ship finally reaches would need to be studied carefully first, its atmosphere tested, its native chemistry, and any potential biology examined cautiously, before anyone risks stepping outside without protection. The ship itself might remain the primary home for years after arrival, slowly emptying into permanent settlements only once the new world has been judged genuinely survivable, closing the loop on a journey that began with people leaving one living world behind and ends, if everything has gone right, with their distant descendants cautiously learning to live on another. Even that slow emptying would likely be handled with great caution, since a population raised entirely aboard a sealed structure would need real time and gradual exposure to adjust to open, unpredictable natural conditions, weather that nobody controls, ground that is not perfectly flat, sounds and smells with no obvious mechanical source behind them. The very first permanent structures on the New World might, ironically, be built to resemble parts of the ship itself, deliberately familiar shelters offering a psychological bridge between the only life anyone aboard has ever known and the strange, open freedom of an actual planetary surface waiting just outside their door. That, in the end, is really what a generation ship is trying to become. Not a vehicle in the way we normally use that word, something built to carry cargo from one point to another, but a genuine substitute for an entire world, compressed down into a structure a few hundred meters across, carrying its own atmosphere, its own water cycle, its own farms, its own power source, its own hospital, its own school, its own government, and its own slowly evolving culture, all sealed inside a hull traveling through the darkest, emptiest environment our species has ever attempted to inhabit. Every convenience Earth provides automatically, quietly, and for free has to be manufactured, monitored, and maintained by hand, forever, by people who never asked for the responsibility beyond simply being born aboard. And if it works, if the air stays breathable, if the water keeps cycling, if the crops keep growing, if the population stays healthy and stays whole, if the knowledge keeps passing cleanly from one generation to the next without ever being lost, then centuries from now, a group of people who have never known any other home will finally look out through a viewport and see a new star growing brighter ahead of them. They will belong more to the ship than to the world their ancestors left behind. And yet they will be the reason the entire voyage was ever worth attempting. Somewhere far behind them, the small blue planet that started it all will still be turning, its oceans still cycling, its forests still breathing, doing quietly and automatically everything the ship spent generations struggling to imitate. None of the people who first imagined that ship will still be there to see it succeed, and yet in every sense that matters, their work will still be running, quietly, inside every breath, taken by someone who never knew their names. And somewhere ahead of them, if everything held together long enough, a second small point of light will finally be close enough to call a destination rather than a dream. No single piece of this project is impossible on its own. We already know how to recycle air, grow crops indoors, purify water, and spin a structure to fake gravity. What has never been attempted is asking every one of those solved problems to keep working together, without pause and without failure, for longer than most human institutions have ever managed to survive on a planet built to forgive our mistakes. That may be the quiet, true meaning behind calling this a spaceship that has to replace an entire planet. It is not really a claim about matching Earth's size or its beauty, since nothing built by hand could ever manage that. It is a claim about matching Earth's patience, its ability to absorb error after error, generation after generation, and simply keep going. If humanity ever succeeds at building such a ship, the true achievement will not be the distance it crosses. It will be the ordinary, unremarkable Tuesday morning, centuries into the voyage, when nobody aboard wakes up thinking about survival at all. They will simply wake, breathe air that has been breathed uncounted times before them, drink water older than their entire family line, and walk out into a curved little world that has, against every reasonable expectation, quietly become exactly what it set out to be. If you found this journey through the ship that has to become a planet worthwhile, remember to like this video and subscribe for more journeys into the cosmos. There are still so many corners of the universe left to explore together, and every one of them starts with a single quiet question worth sitting with. Let your eyes rest now, let your breathing slow, and let the quiet hum of your own small, ordinary world carry you gently into sleep. Sleep well, and until next time, keep looking up.